In this video, I introduce DINOv2 learning visual features on curated data without supervision. Self-supervised image representation learning, pre-trained on large quantity of unlabeled curated data from diverse sources, produces general-purpose task-agnostic visual features, which work across image distributions and tasks without fine-tuning. DINOv2 is a pre-trained visual model based on DINO toward stabilizing and accelerating self-supervised learning when scaling in model and data size. Images from curated and uncurated data sources are further mapped into embedding space as shown here. Uncurated images are then deduplicated before being matched to curated images, as shown here. The resulting combination augments the initial dataset through a self-supervised retrieval system, as shown here, this augmented curated data. The image level cross entropy between the features extracted from a student and teacher networks is applied to train DINOv2 on the created data. Both features are produced from the class token of a vision transformer, as shown here. The DINO loss is defined as here and explained in this figure. This input image, this different crops of the input image, this student network, this teacher network. The cross-entropy loss is used to train the DINO model. Both student network and teacher network use the vision transformer as an encoder, as shown here. The parameters of the student are learned and exponential moving average is applied to update the parameters of the teacher network, as shown here. The patch level training randomly masks some of input patches as input to the student network. The student ibot head is applied to the student mask tokens, and the teacher ibot head is applied to the teacher patch tokens corresponding to the tokens in the student network. The ibot loss is defined as here and explained in this figure, where I is a patch indices of the masked tokens. The parameters of the student network are learned during training, and the parameters of the teacher network are updated through exponential moving average, as shown here. The DINO and the ibot losses use two separate learnable multiple layer perception projection heads, which are applied to the output tokens, and the losses are computed on top. Given a set of n vectors from x1 to xn, a regularizer that encourages a uniform span of features within a mini batch is defined as here, which is applied to minimize the distance between xi and any other point within the batch. Given a query queue and the corresponding keys key and values v, a standard self-attention is defined as a weighted sum of values v, as shown here and explained in this figure. The standard self-attention requires memory for keys, values, and normalization weight distribution, where Si prime is a weight of v and the Si is a score. If splitting the weight Si prime into two terms, the flash attention is computed by using this formulation explained in this figure. In the flash attention, we only need memory to store this S as risk and this V as risk. The computation only requires a memory for a vector V as a risk and a scalar S as a risk, regardless of number of keys and values. We first compute Si and then update V as a risk and S as a risk as shown here. The final attention is exact and no approximation. For more details, please check with these references. Thank you. Bye.